trying to replace is alternative fuel, and which is renewable. And renewable means which comes from biomass feedstock. So we have two categories. One is terrestrial biomass, where is grass and wood can go, and another is microalgae, which goes in aquatic atmosphere. So if we go on aquatic, the productivity is very high compared to the regular biomass, terrestrial biomass. So algae comes on as a winner in among the other feedstock, where which can make transportation fuel, and it can replace diesel or gasoline or jet fuels. So with respect to productivity and efficiency to capture sunlight and produce biomass, microalgae is a kind of very good feedstock when we compare that. Algae can be used to make green gasoline, green diesel or jet fuels. Not only the fuel, we can use to make many other bioproducts, and algae can be used like people have shown how to make polyurethane and many other food supplement materials from algae. The challenges are how to grow it and where to grow it and what species to grow it. Each species has different composition. So which one to do? How to grow it means should we grow in an open pond, in open area, or in a closed photobioreactors? Obviously closed photobioreactor we get more control on a species, and we can really control the conditions, how much oil can be produced or protein or carbohydrates can be produced through certain species, but the cost of cultivation becomes high in case of closed photobioreactors. Let's say if you go on open pond can be a less costly option, but it's difficult to manage the same species, it gets contaminated. So it's kind of a trade-off which one to choose. And when we are looking at algae as a feedstock which can replace fossil fuel or petroleum products, we are really comparing, we have a baseline cost to compare. When we convert algae to green gasoline or jet fuel or diesel, will that diesel or jet fuel or gasoline from algae be same price at what we get petroleum products, or will it be higher? Right now it is much higher than what we get it. So that's the challenge we have to address. So how do we address the challenges? By bringing research in cultivation, harvesting, downstream processing and distribution. I wrote a NSF Career Award proposal for this, solving many parts of the algae downstream processing. So the idea I came out with, algae contains proteins, carbohydrates and lipids, and around that time in 2012 or so, people were focusing on making biodiesel from algae. So you take extract oil and make biodiesel, but rest of the products were kind of wasted or not being accounted for. That's where I thought as an idea that why not we get all the products accounted for, like atom economy, whatever captured in algae, we should be able to use it, or if you cannot use it, we should be able to recycle it. So that was the idea of NSF career proposal which we started, and I got fortunately awarded for this. This is my 5th year on that. So what we showed over the year that once algae is cultivated, we can really fractionate in different compounds, we can make fuel out of it, and when nitrogen or sugars, we can make protein products and sugars out of it. And the process we rely again, when we are looking for alternative fuel, we have to look for the sustainable and green chemistry also. Otherwise, we are getting into the lot of chemicals to convert something. So the challenge of algae is it comes with a lot of water. So my background comes with using water as a reactant and reaction medium. So it's really suited well for algae. Like algae slurry, it developed a process, we call it flash hydrolysis. So it does what it does, it passes through a reactor and it ramp up the temperature of the algae slurry to 280 degrees Celsius or in that range depending on which species, and within 10 seconds it comes out to the reactor. It's a continuous process, and then you cool it down and you get two products. One is lipid products or oil products captured in solid. Another is protein or sugars captured in solubilized in aqueous phase. Now what it does, without use of any chemicals, using the LG slurry, just use of some temperature and pressure, we were able to show that we can fractionate it, and that too in a very short time. That's why we call it flash, that's 10 seconds. It's like putting in microwave and taking out. So this process got a lot of attention from other researchers and industry where they were looking at, and it's kind of going very well. In last 5 years we published 15 papers through this career award, and we showed the industry that we can account for each carbon and nitrogen which is captured in LG in terms of different products. Either it's fuel, or it's a food supplement, or it is recycled back to the pond. Now NSF Career Award in 5 years, then we went back how to show it and demonstrate. So we went back to NSF and applied for partnership for innovation program.
Welcome to Biomass Research Laboratory at Old Dominion University. As a graduate student here at BRL at Old Dominion University, I was part of NSF Career Project. This project has two different aspects, the educational side and the research side. For the research side, we start with a process called flash hydrolysis. This process takes advantage of the characteristics of subcritical water to use biomass, and in particular in our case, as you can see, microalgae. So we have two types of lipid-rich macromolecules that we recovered after flash hydrolysis process. This is biofuel intermediates that we recovered after flash hydrolysis process on Colorado vulgaris. And this one is the biofuel process, the biofuel intermediates that we recovered after flash hydrolysis of Nanochloropsis gaditana with an experiment conducted at 280 degrees C and within 10 seconds of residence time in our experimental benchtop setup that we have in our lab. And besides preserving more than 90% of the lipids in this biofuel intermediates, we also recover more than 80% of nutrients. Let's say 80%, more than 80% of phosphorus, more than 65% of nitrogen content that was originally presented in the microalgae, plus many other minerals that we were able to recover through the flash process. And that liquid phase that we call it hydrolysate can be further converted to fertilizers like strovite and dismurate, as well as hydroxyapatite, which has a biomedical application like synthetic bone, dental filler. It can be used, as a catalyst, even using for hydrothermal liquefaction or many other, applications. And we proposed two pathways in order to convert that nutrient-rich hydrolysate to these two value-added components and products using the process of hydrothermal mineralization and ambient, or we can say atmospheric precipitation process.
My research at BRL involves recovering value-added byproducts from the liquid hydrolysate. The sugars from the hydrolysate can be used to create fuels such as ethanol or butanol or chemical intermediates, and then the organic acids can be used as food additives, cleaning supplies, or again chemical intermediates, and then the proteins and the fatty acids can be used for pharmaceutical or nutraceutical purposes. My current research involves incorporating dilute acid to the flash hydrolysis system to recover sugars. I'm trying to optimize the process with lower temperatures than our previous studies and at lower operating pressures.
After getting good results from lab scale studies through our NSF career grant, we published a lot and we presented to different conferences. But what next? So we thought, why not build a pilot scale which can be demonstrated to the world, can go to different sites and show the flash hydrolysis technology which can be used for different purposes, fractionating different fractionated components of algae. I went back to National Science Foundation, applied a program called Partnership for Innovation. That's a kind of technology translation. So I applied for that grant and fortunately we got awarded. So now under that program we are trying to make a demo scale facility which is same flash hydrolysis continuous process in fractionation in few seconds. We are putting on a mobile unit such that we can take it to different places and show that what this technology can do. So in that, this about 2-year grant, and there are a lot of innovation is required because we showed this in lab scale facility, but the thing is we are not using direct algae slurry pump. We are trying to use a piston system to inject slurry in the reactor, but now we are buying real pump. We are buying real heating system. Heating system is a challenge. It's easy to say heat in 10 seconds and then you can fractionate it. But how do you heat biomass slurry to the desired reaction temperature in 10 seconds and then how you cool it? A lot of thermal analysis is involved and a lot of innovation is involved. So to bring the user on board that this can be scaled up, we are building a pilot facility, and that way we are very much near to completion of that facility, and we should be able to show that run that by July of this year.
We chose to make our pilot unit mobile so that we can bring it to different sites of industry, different algae locations such as farms or even algal blooms to demonstrate the flash hydrolysis process. Some of the design challenges we faced in scaling up our mobile unit is our heat source. We chose induction heating to rapidly heat our algae slurry through our mobile unit and really produce that short residence time that we're looking for in flash hydrolysis. In order to find a pump that can fit our various needs, we face several challenges.
To handle this, we contacted more than 75 vendors to figure out how we can get the right pump for our process that can handle microalgae slurries with a solid content of 10 to probably 25 weight percentage that will be as viscous, have a viscosity of around 175 centipoise to the with a flow rate that is in the range of 2.5 gallon per hour, and plus to the high pressure, approximately 2000 psi of the reactor that we're interested to do our process. So that was not something easy. We come up with multiple options that they only can handle much higher flow rate, let's say what is expected as a flow rate in large oil companies and petrochemical refineries, but not in the pilot plant study that we were interested in. So we asked them for a custom design pump to be able to handle our process.
As a civil engineer, I was able to receive the opportunity to work as a RU in the biofuels lab. And since the class was something I didn't know of at the time, that was taught by Dr. Kumar, I figured that I could go ahead and try to get more of a hands-on experience working in the biofuels lab. And it actually helped me understand more, especially about cultivating algae, which I had no knowledge of in the beginning. But after a lot of trial and error, it was much more simple than I thought, and that's something that I could definitely use when going forward with potentially getting a major in environmental engineering. This lab experience has actually taught me how to cultivate algae, which I never really had the opportunity to do before. And I was also able to use more chemicals than I've ever used in any other lab setting, and I learned more lab etiquette. And I actually also learned how to do a proper analysis with algae. The things I've learned being in the lab is cultivating algae and using analytical techniques such as total suspended solids, which require the use of various instruments within the lab. And I've also learned how to use different chemicals to create media that will help the algae grow properly. The objective of my research was to determine whether or not algae can grow within fish wastewater. And in conclusion of the project, we were able to determine that the algae grew much more sufficiently compared to the media that we had used as a control.
The Biofuels Research Apprenticeship Program, or BRAP, is a 4-week intensive program where local high school students come to the ODU Biomass Research Lab to learn about basic laboratory procedures in the environmental labs. We teach them algae cultivation and also how to use basic skills in the laboratory. During those 4 weeks, students learn algae cultivation, analytical techniques, and basically how to function in the environmental laboratory spaces. They'll be fully equipped to know scientific knowledge about biomass, waste-to-energy research, and basically everything all of us do as graduate students on a daily basis. The major goal of the Biofuels Research Apprenticeship Program is to support and promote STEM education. The BRAP program is supported through the National Science Foundation.